All right, this time we're going to do a Desmos activity called Central Park. This is one of maybe, if not my favorite Desmos. I love this activity, but it's hard. So let's talk about it. So first, what it does is it makes you just sort of try to like guesstimate where you could put the dividers to make 4 equal parking spaces. I'm terrible at this. I'm going to get it wrong. Let's see. Maybe no. Like there. So this one should be right in the middle, right? So maybe right about there. All right, let's give it a shot. Okay, so the first car fits, second car fits, third car fits. Oh, wow, I can't believe I nailed it. All right, so what happens if you get it wrong though? Like let's say I was off by a little bit here. That car fits, that car fits. So I'll probably fit the one on the end, yep. And then the guy in the middle, he gets all mad because he can't fit. I don't know, I love that. I think it's great. All right, so don't get too stuck on this. If you can't put it in the right spot or whatever, don't worry about it. It's not like a required thing. The whole point is to show you that it's supposed to be hard to eyeball things like this in a Desmos and in real life. Somebody who was going out to paint parking spaces in a real parking lot, they wouldn't just eyeball it. They would measure it and probably use some math. Okay, so they want us to try it again. Let's see if I can get lucky. It doesn't matter if I do or not. I'm gonna continue on to the next activity regardless of what happens here. Maybe I'll move this one a scooch over there. All right, let's try it. Let's see. Boom, boom. Nope, I must have messed up or else they'd have put that car there. So he got in all tilted because he had extra space. He was like, oh, this parking space is wide. All right. And we're gonna try one more time. So this is for boats. So if we were building the dock where people are gonna park their super expensive, fancy boats, would we just eyeball it? Would we just let it be up to how good we can guesstimate? Oh, I guess maybe I could. But in real life you wouldn't, right? You would measure it and you would do some math and make sure you get it perfect because that's your job, and people's ability to park and put their expensive cars and their expensive boats in the right spot without dinging each other, without hidden doors and stuff. That all depends on you being able to paint these things right. So let's do it the right way. It says, suppose you wanted to figure out the exact space between these dividers. What measurements would you need? Well, what you would need is let's see here. Let me draw on here so you can know exactly what I'm talking about here. You'd need to know, how wide is this? In other words, the width of your total space. That's what I think I'll call this for the rest of the time. The whole space that you have to work with to break up into smaller parking spaces, I'm going to call that the entire width or the whole space, something like that. We'll probably wind up calling it W for the rest of this activity. So I would want to know the width. Oops. Width of the entire space, not just of one parking space, right? Because that's our job to figure out. It's our job to figure out what the space between the dividers should be. So it wouldn't make sense to say I want to know the space between the dividers in order to find out the space of the dividers, right? So we can ask for the whole space across, and unfortunately, we're not just dividing that space evenly into 4 chunks, right? Because we have to consider these divider things. These things here. You know, I should probably use a different color than blue since it's on blue water. So the width of these things here, why are you doing that? I want to know how wide is this and this and this. I'm sure they're all the same. And so these are called dividers in this activity. So I'm probably going to use D to refer to each of these things. And the width. Divider? Is that spelled right? Yeah, I guess so. Okay. So let's go with that. All right, and so they give us exactly that. Now it's our turn to do this using a little bit of math here. The dividers are each 1 foot wide, and the total parking space here, the width of the whole thing, is 35 feet. All right, so it's our job to figure out how wide is this space supposed to be. Well, I would just take 35. I would subtract the dividers, which there's 3 of them, and each one of them was 1 foot. So that's 3, and I would get 32. Then, what I know now is I have 32 feet of actual good space to work with that I'm going to divide into 4 parking spaces. So I'm going to do 32 divided by 4 equals 8. So I would want 8 feet between each one. Now, in my opinion, that's a lot easier and a lot more precise and reliable than just eyeballing it like we were doing before. All right, so let's do it again. The process stays essentially the same. We're going to look at that total width across the top, which looks like it's going to be 48 this time. Let's use this color. Okay, we've got 48 total width to work with, and we have 3 dividers, each of which are 2 feet wide. So let's do a little easy little scratch work real quick. We've got 3 dividers, 2 feet each. So they take up a total of 6 feet, right? Well, 48 total feet to work with minus the 6 feet taken up by the dividers equals 42. I got 42 good feet to work with. So I want to divide that into 4 equal spaces. I'm going to do 42 divided by 4. Well, I know if I was doing 40 divided by 4, that would be 10, right? That's an easy question. So really, I just need to add on whatever 2 divided by 4 is, because I got 42 instead of 40. Well, 2 is half of 4. So that means I need to add on an extra half. So I'm going to go with 10.5. Boom, nailed it. All right, and last one here. I think this is the last one. Let's see. Let's use purple. This time we've got a total width of 41 feet, and our dividers are 6 feet. So we have 3 of those dividers, right? So let's do a little scratch work off top first. We have each divider 6 feet. We got 3 of them. 6 times 3 is 18. So we're losing 18 feet worth of good space for these dividers. These have to be wide because people are walking on them, right, to get out to their boat. So that's why these are wider than the ones for the cars. Okay, so let's take our 41 feet that we have to work with. Let's subtract the 18 feet for those floating, walking things, whatever. I don't know what people call them. And we get, what is that, 23, right? 41 minus 10 is 31. 31 minus 8, 23. All right, and so let's take that 23 feet and let's divide it into 4 equally usable spots there. Well, I know that if I was doing 20 divided by 4, I would get 5. And then 3 divided by 4, that's 3/4, aka 0.75. So I'm pretty sure this is 5.75. I hope I didn't mess that up. Let's see. Let's punch it in. So how does this connect to the algebra that we're doing in class? Why is this one of Mr. Thomas's favorite activities, especially to do when we're starting to learn algebra? Well, if you can figure out these solution strategies that I'm using, I'm gonna subtract the dividers, and then I'm gonna divide the remaining space in order to create the right space for the parking spaces, then you can solve equations that are set up the same way. Look, I'm gonna set up an equation for this setup here. The equation would be, well, we know that the dividers are, oh wait, you know what? No, I'm not going to do this yet. I'm pretty sure this activity gives me a chance to do this later on a separate screen. So I don't want to get ahead of myself. Let's look. All right, so Ebony was working on the previous screen, and she wrote this expression for the width of each space. 41 minus 3 times 6 divided by 4. Is our expression correct? That's exactly what we did. That's the correct solution strategy. You might be thinking, well, wait, like what's with this big fraction bar? So when you put multiple things on top of a fraction bar, like you see here, the 41 minus 3 times 6, all on top of a fraction bar like that, these things are grouped together. It's almost like they have a invisible parentheses around them. It kind of says, hey, you got to do this math first, and then you can divide by 4 at the bottom, unless you want to do the trickier way where you're dividing everything by 4, and that gets ugly really fast. So that's the first thing we did, right, was 41 minus 18, which that's what 3 times 6 is, and then we divided it all by 4. So yeah, I think Ebony's got it just about right. So explain what the 3, the 6, and the 4 mean in this situation. So the 3 came from the fact that we have 3 of these floating divider things, right? We're always taking the width of the divider and multiplying it by 3 to figure out how much total space we're like losing because of the dividers. The 6 was the width of I'm going to say of each divider. All right, so we take number of dividers, multiply them by how wide each one is, we get the total width of them. And the 4 is the number of spaces we wanted to create. So at the end, we wind up dividing that leftover space by 4 to create 4 evenly sized parking spaces. So yeah, here's where I wanted us to get to. So it says, write instructions for how to calculate the width of any parking space with 3 dividers. So if you have 3 dividers, you always wind up with 4 parking spaces, right? That's a little tricky when you first think about it, but three dividers makes 4 spaces, right? If I draw 3 dividers up here, 1, I don't know why that got all diagonal, 2, 3 dividers, you wind up with 1, 2, 3, 4 spaces. All right, so look, they're using the same letters that I said we were going to use. They're marking the total distance across the top with the letter W, and they're marking the total width of the dividers with a D. Let's define those variables up here at the top. Total width, D equals width of dividers. And so there's like 2 things that I really hope students learn from this activity. The first is that you went through the same process over and over again of figuring out how wide the spaces should be, right? First thing we did was multiply so I'm not going to write all this out, actually, that would take too long. But first thing we did was we would multiply the width of the divisor times how many dividers there are, because we needed to know how much space that would waste from the total space we had to work with. And so that's 3W, right? 3 times, because there's always 3 dividers. Sorry, I meant to say 3D, not 3W. 3D is the width of the dividers. Okay, and then we would take that number once we got it, like for this one it was 18, and for this one it was like 6. We would take that number and we'd subtract it from the total width that we got up at the top. So that is now being represented by W. See, I'm not using the numbers anymore. I'm not punching in a 2 from this one, or a 6 from this one, or a 35 from up here. I'm writing instructions how to do it for any width of space and for any width of divisors. And that's why I'm using a W to represent the width of the space and a D to represent the width of the dividers. And so now anybody who looks at my equation here, I guess more of an expression, will know how to do this. They're going to know, okay, I take the width of the total space, I subtract 3 times the width of the divisors, and then I divide all of that by 4 to make 4 spaces. Oh, but you know what? I wasn't even supposed to make that equation yet. I was supposed to just type it out here. So multiply the, so I should have been writing this out while I was talking. Dang it. All right, multiply the width of dividers by the number of dividers, not divers, dividers. Subtract that number from the total width. Then divide that number by 4. And that's what my equation here is. And so I hope that students see that, oh, when you write equations like this, you're essentially just giving someone a set of instructions they could follow, right? Like someone could come along and read this, and as long as you've defined the variables, you put somewhere up there that W is the total width, D is the width of dividers, they can look at this equation and say, oh, my instructions are take the width, subtract 3 times the width of the dividers, divide by 4. And if you get good at reading this stuff, it's like having a new language that you can speak. All right, so this one's asking for the equation here. If you're coming into this video just to learn about this question and you want a good explanation, rewind a little bit because I actually explained it on the previous screen. And so on this one, I'm just gonna type it. What you need here is the width of the space, S, is gonna equal the total width of your working zone, whatever, minus 3 times the width of the dividers, and then you want all of that divided by 4. Let's see here. Now, so this is gonna oof me up because what I did is I pressed slash on my keyboard and it didn't do everything I wanted, right? See how it only put the division symbol underneath the 3D? I don't want that. I don't want to take the width of 3 dividers and divide that by 4 and then subtract that from W. Like that's what this says, right? This says do the 3 times the width of the divisors, divide that by 4, and then subtract from the total width. And see how if you look at the diagrams here, my parking spaces are all messed up, they're not right. What we have to do is make sure that the dividers are getting subtracted from the total width first. And that's where our friends, the parentheses, come in. But this right here would be wrong. We never put parentheses around an entire equation. It almost doesn't even make sense to do that. So instead, I want to make sure the parentheses around my width minus 3 times the dividers. Then if I do a slash for division, Desmos knows that I mean to put that under that whole part of the expression. Boom. And now all the parking spaces for all the different like little questions we did along the way are going to turn out right. And so here's the other thing that I really want students to come away from this, this activity with, is think back to our solution strategies for each one of these. For each one of these, no, you know what? I'm going to save that for a different day. Don't worry about it. If you can figure out how to write the instructions, you're good. Like if you could figure out how, if you understand like how the equation matches the math that we did over and over and over again, that's what I mean. That if you understand that part, that's good. Okay, so they want to give us a little extra challenge here. The only difference really here is that there's 2 dividers making 3 spaces rather than 3 dividers making 4 spaces. But the similarities, it's basically the same thing, right? We've got a total width to work with. We got dividers making spaces. I'm sure you can fill this one out without my help. So here's the challenge one. It says, use a variable to write an equation for the perfect width of each space. And we've got all these variables we have to work with now. So before, it was the only things that changed was the width of the total space and the width of the divisors. So we only needed two variables, w and d. But now other things are able to change. The number of dividers is able to change. So because something's able to change, we assign it a variable, n. And then now the number of spaces we need is also allowed to change. So we assign that a variable, m. All right, but all we're doing now is writing the exact same expression or equation, whatever you want to call it, that we had a couple screens ago, except our previous one was this. You should have written S equals W minus 3D all divided by 4. Right? Well, look at where some of these pieces came from. So this is still the width. This is the width of the dividers. This right here was the number of dividers, right? But there was just always 3 dividers, so we just put a 3 there. And then this was the number of spaces we wanted. But there was just always 4 spaces, so we just put a 4 there. But now those things are able to change, but we just put the variables in the same spots that they're in. And so that someone could use that as a set of instructions to say, okay, no matter how wide it is, no matter how wide the dividers are, no matter how many spaces I'm trying to make, no matter how many dividers I got, if I follow these instructions, I'll be okay. I'm going to take the width, I'm going to take that width, and I'm going to subtract the number of dividers multiplied by the width of each divider, and then I need to divide by the number of spaces I need, but I got to use parentheses to make sure that I do that subtraction up there first. That should work. Let's try it. Boom. I don't know that I've ever looked at this screen before and all the times I've done this activity. Let's see here. Here are the variables from the previous screen. Julian says he wrote an equation for the width of a parking space, but didn't use m at all. Is that possible? Right off top, I think no. Like, I gotta look at this for a second and see if there's something I'm not thinking about. It doesn't seem like that should be possible, unless there's something I'm not thinking about. Oh, yep. All right, I see how you could do it without using n. Notice that, without using m, I mean to say, notice that however many dividers you have sort of forces how many parking spaces you create, right? If you have 1, 2, 3, 4 dividers, you wind up with 5 spaces. 1, 2, 3, 4, 5. If you have 2 dividers, you wind up with 3 spaces. 1, 2, 3. If you have 3 dividers, 1, 2, 3, you wind up with 4 spaces. 1, 2, 3, 4. In other words, you should notice the number of spaces is always 1 more than the number of dividers. In algebra, we would write that as this. The number of spaces m is equal to the number of dividers plus 1. It's always worth 1 more, right? Well, that means that anywhere we were going to use an m, we could replace it with n plus 1 if we wanted to. And sometimes this is a really good thing that you can do in your equations, especially if you're like programming a computer or writing like some function that a machine is going to use or something. The fewer variables you can use, the better. If you can write one thing in terms of another, notice I'm telling my equation or my machine or my computer how many spaces we need relative to how many dividers we have. And that makes things more efficient and easier to understand. So I'm going to just write so I guess I thought it was going to give me a space where I could like actually write the equation out. The equation, if you're curious, should look exactly like the previous equation, just with an n+1 at the bottom instead of an m. It should look like, what do we get? W minus number of dividers times width of dividers, all divided by, instead of an m down here, it'd be n+1. And so explain your thinking. The number of spaces is always one more than the number of dividers. Boom. All right, I think we got it all done. See ya.